Okay, now we're ready. So let me go share, start sharing. Oh, there's another question. How long do you think the test will take to grade? Okay, I mean, today and tomorrow probably. It depends because online test is a little bit. I mean, I need to look at each one of your. I mean, it shouldn't take that long, but let's see. Maybe I think I should get some time today to grade it. So, yeah, I think that maybe the worst scenario by the end of tomorrow, I should be able to finish all the grading. Yeah. Does that sound good? You guys eager to know the grade, I guess. Okay. Again, when we talk about chapter 4 in this week, and that's laws of motion, and we're interested in the question of dynamics, which is explaining motion, and we got 3 laws of Newton's. That's the basic dynamical law in mechanics. First, second, and third. The most important one is the second law, F equal to ma. So our task here in this chapter is to learn all the forces we normally have, and then apply those forces to the equation to get the to get the expression and all the other information. So, and then the first law is kind of like a special case of the second law, and then the third law is just a case for 2 objects interact with each other, you know. So, and then we talk about the forces, right? Gravity, normal force, and tension, and then friction, okay? And these are basically common forces we have. And then we did a bunch of examples. Again, I think those examples are important for you to study because they kind of they go in order from the simple ones to difficult ones, you know, and then it can help you to see the main procedure, and this same procedure repeat again and again. So in these 5 problems, okay. So I'm gonna go ahead and do another example, and then we'll do the exercise, okay? I'll let you guys do some exercise. So today you can get some bonus points. So the example I'm gonna show you is actually here. This is a book I got from 9th edition. Okay, so the number in your 11th edition might be different, but I think it's a good example. So I want to bring it up to talk about it. So this example is called weighing a fish in the elevator. Okay, that sounds like a crazy scenario, a case, you know. But it's very interesting in physics. Okay, so what happens here is a woman trying to weigh a fish with a spring scale attached to the ceiling of an elevator, like what is written here. And so when the elevator is at rest, the fish weight 40 Newton. Okay, the question is, what weight does the scale read if the elevator accelerate upward at 2 meters per second square, or accelerate downward at 2 meters per second square? Okay, so these two are, these are the questions. Okay, so let me go back to my I think we have this. Hold on, draw. Okay, maybe not. I think I like the blue one better. So let's go back to the blue one. Wait. Oh, I forgot to attach this. Okay. So what we're given here are very simple information. Okay, first of all, we know that when the elevator is at rest, okay, the fish, okay, so this is the scale, and then this is the fish. I guess I don't need to draw the woman here. Well, maybe I can. This is the best I can do. Okay, so at rest, the fish weight, the number read from the scale is 40 Newton, okay? Now the question is, A, when there's acceleration going upward with 2 meters per second square, A equals to 2 meters per second square going upward, okay? What's going to be the reading? And then B, reading. I apologize for my writing. I need to definitely check my pen. I think there's something wrong with it. And then going down with 2 meters per second. Going downward, okay, reading. Okay, so these are the two cases. And so first of all, without doing any calculation or anything, let me just ask you based on, okay, I got a message. Hold on here. Oh, okay, somebody has a bad connection. I'm really sorry for that, but hopefully, okay. So let me ask you this question: do you think that the reading will be the same if there's an acceleration going up or going down? Just send me a message, okay, saying whether you think it's going to be the same.
Isn't there less gravity the higher up you go? So, like the effect of.
Oh, you're saying that because the elevator is high, gravity G is less, right? So that's what you're saying?
That was the idea behind what I said, yeah. But
yeah, that is I mean that's true, but it really doesn't really matter much for this case, because see, unless you go to a mountain, you know, because that's, remember the way we calculate our G is this: G equal to capital G times RE, capital G times ME over RE squared, okay? So if you go higher, you need to get a little bit larger radius here, but the radius of theirs is really large. It's like 6,000 kilometers or something. Well, if you go on elevator, even for a tower of like 100 floors, okay, it's only add that up to like 300 meters or something. That's nothing comparable to 6,000 kilometers. So unless you go to a mountain, you know, like a couple thousand meters, you know, like couple kilometers, you feel like a little bit difference, you know. For example, if you well, when you go higher place, the G is a little smaller, and then the pressure is a little lower, temperature is a little lower, and everything. But even that, the G is really, really close to this number, because mostly this is really large. Okay, so we're not talking about that effect. We're talking about actually a different effect. Okay, now I got a couple answers. Two of you guys saying no, it shouldn't read the same. One of you guys saying yes. Okay, now I mean, again, you should have a reasoning for this, right? For people who don't think this is going to be the same, why do you think it's going to be different?
Would it have to do with Newton's like equal and opposite forces? So like there's an opposite force acting on the fish.
Okay, opposite force.
So like if it's going up, the fish would be like pulled down.
No. That's probably a little bit misleading. Okay, I know like people saying that if you have an elevator that's actually going up, you have additional force or something, but that's not really what we talk about. So anyway, let me go ahead and, I mean, keep that in mind. Let me go ahead and talk about this. Okay, so I mean, again, to answer those questions, there's two things we need to figure out. First, what is actually measured on this scale? Okay. So, I mean, as you see here, right, the scale is connected to a fish like this by a piece of string, okay, or a hook or whatever. But what is really measured is not the weight of the fish, but the tension in the string. Do you agree? Actually, same thing, whatever scale you use, right? For example, if you use a table scale or a bathroom scale, like at home, you stand on top of it. What is really measured is not your weight on the scale. It's actually the normal force, okay, on the scale, okay? So anyway, same thing here. What is really measured is the tension, okay? So what you read out here is the tension in the string. So it may or may not be the real gravity, real weight of the fish. Now, to see whether it's real weight, let's do force analysis to the fish, okay? So I'm gonna draw this box here. This is gonna be my fish, okay? It's an approximation, it's a box, rectangle box. So there are two forces on the fish. Okay, one is the gravity. Remember, there's always gravity there, right? mg. Okay, maybe I'll call it W here in this case, W, the weight. The other one is nothing but the tension, right? The tension on the top, so it's going up. So we got these two forces, and there's nothing else. Again, remember, there's always weight, and then after that, look for contact. Okay, this contact we have here is just from the string, so that's the two forces you have. Okay, and what else? So so that determines everything. So there's these two forces. If you set up a coordinate system, you can put this as your positive direction going up, like y, and this will be your x, like this, right? So and these two forces are already on the on the y-axis, so you don't need to worry about the component or anything, right? So let me, I mean, let's say first, when it's at rest, right? At rest means, okay, if you apply Newton's law to this, you have total force equals to mass times acceleration. In this case, we only worry about the y component, okay? So total force you have is gonna be tension minus weight, because the weight is going negative direction. Well, in the first case, when it's at rest, there's no acceleration, so this is gonna be just 0. So that gives you tension equals to weight, right? So that means the tension measured when it's at rest equals to the weight. So so that means the 40 Newton here you got here is nothing but the tension. I mean, it's actually the real weight as well. So it's so the real weight of the fish is 40 Newton. So when it's at rest, okay. Now let's look at the first case, okay. When there's acceleration going upward, okay. Now the forces does not change, right? It's still these two forces, T and W, going up and going down. But the acceleration now, you have an acceleration going up like this, right? So what does that tell you? It tells you when you write your Newton's law here, on the left-hand side, you still have these two forces, but on the right-hand side, you have an acceleration, right? So it's gonna be like T minus W equals to ma, okay? And you, because A goes to upward in the second case, so it's positive, right? So in this case, your weight equals to T minus ma. So as you see here, your weight does not equal to the tension anymore, okay? So, okay, sorry, yeah, maybe let's do the other way. So the tension equals to weight plus ma. So the real weight of the object does not change, but because the object is moving upward with acceleration, the tension is bigger than that because of this thing. So you have okay, so to solve for the new tension, right? Which is what the scale is reading. You need to add the weight to this piece, okay? So what is this piece? Okay, you're given the acceleration, which is 2 meters per second squared, but you don't know the mass, but you do know the weight. So you can calculate the mass from the weight, okay? Remember, weight is defined as mass times gravity g, right? So that means mass equals to weight divided by g. So that is actually 40 Newton divided by 9.8 meter per second squared, okay? Let me see, yes, we're doing that. Okay, so from there, you can solve for the mass, okay? So 40 divided by 9.8, okay? So you got 4.08. I'll put it like 4.1 kilogram, okay? And then you know everything. You can solve for the tension. So tension equals to W plus ma. W is 40 Newton. And then the mass is a 4.1 kilogram. Oh, sorry, this is a plus. Let me erase it. Okay. Okay, plus times acceleration, which is a 2 meters per second squared. This is the real acceleration, okay? 8 is 2 meters per second squared because going upward, so it's positive, okay? So this together, combine it together, right? The second part you got 8.2, so you got 48.2 Newton, okay? So as you see here, when the elevator is accelerating upward, the tension is bigger than the actual weight. The reason for that, I mean, if you try to understand it, right? Going back to here, right? See, the reason for that is the total force need to provide an acceleration. So the force going up has to be larger than the force going down, because the tension here does not need to only compensate for the weight, but also need to provide the acceleration going up. So it need to be bigger so that you can have a total force going upward, okay? So that's why you have this 48.2 Newton, okay? Does that make sense? Give me a thumb up or something, you know, if you feel like it makes sense. Good, okay, good, okay, okay, good. Okay, so now the second problem is that the second part is actually similar, right? In this case, you have acceleration going down, right? It's still like 2 meters per second squared, okay? Now, you don't need to change, even need to change your formula. It's still like this formula because you have same Newton's law, T minus W equal to MA. So you have T equal to W plus MA. But in this case, because acceleration is going downward, so it's a negative number, okay? Because the positive direction, as we defined, is going up. So this is negative. So you have 40 Newton plus 4.1 kilogram times negative 2 meter per second squared, okay? So that's the second part here, okay? This A here is negative, okay? So, and that gives you the whole, the answer for this one. So you have 40 minus 8.2 instead of plus 8.2 in this case, okay? So that means you have a 31.8 Newton in the second case, okay? So the tension in the second case is smaller. Now, why is smaller? Again, going back here, okay? In this case, I mean, the second case, the tension need to be smaller than weight because the whole thing is going downward with acceleration. So the total force need to be going down so that the force can provide you the acceleration. Does that make sense? So again, I think, a good way to think about everything now is to keep in mind this Newton's law. You have the total force on the left-hand side, you have mass times acceleration on the right-hand side. So in this case, it's like we kind of doing the backward. We know the acceleration, so that kind of give us a constraint about what total force we should have. If the acceleration going up, the total force is going up. If the acceleration going down, the total force is going down. And then this determines the tension on the string. It may be bigger or smaller than the weight of this fish. Good? Okay, good, yeah. I mean, again, it's really good to see you guys' face, you know, even though you don't, there looks like you don't, I mean, yeah, it's even better. I can see you're smiling, you know. Sometimes it's in the morning, you know, you guys kind of still a little tired or something, but a smile means a lot to me, you know. Okay, good. So with this understanding, let me ask you a third part, okay? Well, this is a tragedy here, okay? What if the cable of the elevator is broken? So if the cable of the elevator is broken, what's gonna be the reading in the scale based on your understanding of the previous two parts? Again, this is not an exercise, but I want you guys to maybe take a minute to think about it, okay? If you don't know the exact reading, tell me at least, is this gonna be larger or smaller than the actual weight? Okay, I got some answer here. Okay, small, okay, good. I got two answers so far. It's an interesting case to think about, right? Okay, good. But I mean, it's probably not good for the woman in the elevator if the cable breaks, you know. So I mean, we could think about this in two different ways. One way to think about it is still use this the formula we have here. Okay, so remember when the cable is broken, right? What's going to happen? What's going to happen is the whole elevator is going to do a free fall motion. Okay. And the fish is definitely going to fall with the elevator together because everything is doing the free fall here, okay? So the fish is going to fall together with elevator. So you have a acceleration equals to negative 9.8 meter per second squared. That's the free fall acceleration, okay? Yeah. Yeah, somebody mentioned there's like a movie when the cable breaks, everyone in the elevator hit the ceiling. Well, will that happen? Yeah. I think so. Yeah. So okay. Anyway, you will do it formally. You have a equal to negative 9.8. So using the same formula we had here. Hold on. Let me close this window here. Okay. Use the same formula we had here. We can solve for the tension. So it's going to be just W plus MA. Now W here basically going to be like same 40 Newton here. And then you have mass, which is 4.1 kilogram times A is negative 9.8, okay, meter per second square, okay. Okay, so this case, the second term becomes actually mg, but we know, I mean, with a minus sign, but we know that equal to weight, right? So this subtract that, we give you exactly 0. So in this case, there will be no tension in the string, and some of you answered it right. There's a tension will be less. It's going to be 0. Why is that? Okay, because in this case, the fish is going together with the elevator in a free fall motion. And so the total weight on the fish need to provide the acceleration for the motion so that there's no tension at all. Because if there's a tiny bit of tension, the total force will be smaller than the weight. And then the acceleration you got on the fish would be smaller than the acceleration. So the fish wouldn't be able to go together with the elevator. So it turns out that in the end, the tension will be just 0. Everything's going to go. Now, what you would observe here is, if it really happens, hopefully not for you, but what would happen, what you see here is going to be that when the cable breaks, everything go to the ceiling for a second, and then they will just stay they can float basically in the elevator because they're falling together with the elevator. Okay, so it's actually going to be the same as you're going to see like if you do parachuting. Who does parachuting? Nobody, right? Yeah, I didn't do that, but you probably see those videos, right? When they jump out of the airplane, right? They just seems like they're floating in the air, you know, and they video each other. You see those people, they're just floating, you know. They're not really floating. They're all accelerating downward with this free fall acceleration. Just from each other's point of view, they're floating because they all fall together. Does that make sense? Yes. So so basically, it basically saying that if you hold a ball in your hand in that elevator and then the elevator cable breaks, you release the ball. What you're gonna see is that the ball is gonna float in front of you. It seems like some mysterious force is balancing gravity from your point of view, but actually nothing like that happened. What really happened is you and the ball goes together. You know, you both go down. That's you're both falling. You know, that's what is happening. So I think this is an interesting problem. You know, this problem is not hard in terms of math, in terms of algebra, right? We have just the forces along the single direction, but it's actually kind of an interesting problem to think about. You know, you can see what is really the physical meaning of the total force, and then in terms of producing acceleration, et cetera, et cetera. So okay, so that's about this. Okay, any questions about this problem? Okay, today we have plenty of time. We have 45 minutes, so we'll do some exercise. Again, the goal of this exercise is to help you to master whatever we're learning, especially because of the interruption of this test. You guys may not be focusing on Newton's law in the last couple of days, but it's a good time for you to kind of focus on this right now and understand what's going on. Again, as I said, this chapter is supposed to be the most difficult chapter in the whole book, okay? So if you feel it's a little bit challenging, that's totally normal because that's supposed to be the case. After this chapter, things gonna be a little bit easier, okay? So let me start from some examples, okay? I mean, exercise, okay? Again, you get some bonus point by doing that. So let me make it a little bit short, smaller. Okay. So let's start from the first one. Okay. So we did bunch of exercise example. So let's do some exercise about another kind of force called tension. But the ideas are really similar. Okay. So the first one here is going to be like this. So you have a ceiling and then a piece of string, and then there's a object hanging on the string at rest. Okay. So you know the mass is 3 kilograms. Okay. So the first problem is like calculate the tension. Okay. Tension in the string in this case. And then the second one here is, well, now you have a string that's, I mean, you have something pulling the object. Let's call this a tension T. Okay, the whole thing goes up with an acceleration A. Okay, equals to 3 meters per second square. Okay, let's calculate the string in the tension in the string in this case. Okay. And then the last one we want to do here is a little more complicated. So we have a ceiling here, and then we have 2 pieces of string going from 2 different parts, and then at here there's an object here. Okay, now let's say again. Okay, again this is a mass equal to 3 kilograms, and then the last one here the mass is 3 kilograms as well. Okay, sorry. Oh, why is it always pop up? Okay, the mass is 3 kilograms. And so you have the 2 pieces of string here, okay? And then let's say the angle here given as 30 degrees, okay, for each one of them, okay? So let's try to calculate the tension in the string, okay? Now there's a 2 pieces of tension because there are 2 pieces of strings, but because of the symmetry here, you're supposed to get the same tension on both 2 pieces, okay? So, okay, I got a message here. Oh, that's okay. Let me answer that. Okay, so these are the 3 problems. So go ahead and do them. Oh, I have a question about the previous example. It says the weight was 40 Newton. Was this given? Okay, let me go back a little bit to explain that first. Okay, so see in the problem, what is given is when you weigh the fish at rest, the reading is 40 Newton. Okay, but as we explained, because the reading, what is reading here is the tension in the string. But when it's at rest, the total force equals 0. So the tension equals to the weight. Okay, so from there, you can conclude the weight is 40 Newton. Although it does not just tell you the weight is 40, but it says the weighting, the reading is 40. So that's actually, so that's how they give you the information. Okay, and that's why normally when you weigh yourself, you on a scale or something, you got your reading because there's no acceleration. Okay. So as you see here, right, the tension is larger when the elevator goes up with acceleration, and it's smaller when the elevator goes down. So if you want to lose some weight, okay, instead of going to the moon, another option is to measure yourself, weigh yourself in the elevator that's going downward, okay, and then you'll get a smaller weight, okay. Bring a table scale next time, or fast scale to the elevator, try it, okay. Take a picture of your weight in there, put it on the Instagram or Facebook, then show off to your friend. You lose some weight, it'll be cool, but you don't need to do any exercise. Okay, so let's go back to this. Okay, so again, we have these 3 exercises. Yeah, please start from the first one. Okay, so let me talk about this together. Okay, so I'm sorry, my son is next to me. He want to get some help from his math problem. So I was distracted a little bit from him. So let's do this one by one, and let's do it slow, and so that you guys can see how everything's done. So the first one, right? start from a free body diagram as we always do. So again, the first force is always gravity. So put mg here, and then there's a and then you look for contact. One contact here, so you have tension going up. So you have two forces balance each other. I mean, and then it says at rest, right? So you set up a coordinate system, and in this case, you only need to worry about the y coordinate. So let's just draw the y coordinate, okay? So at rest, so that means according to Newton's law, T minus mg equals to ma, which is 0 because a is 0. So from there, you got T equals to mg. So plug in numbers, you have 3 kilogram times 9.8 meter per second square. And so that's very simple, right? This is like 29.4 Newton, okay? So this problem is really similar to the one we solved for the normal force case when you have a block putting on the surface, right? And everything at rest. So it's a very simple problem. But again, keep in mind, this is a procedure, right? Free body diagram, coordinates, and then write down equations based on the coordinates. Okay, second one. It's the same, but the only difference here is you have tension going up and mg going down. The only difference here is you have acceleration equal to 3 meters per second squared. That's positive, okay? So that means when you set up Newton's law, it becomes T minus mg equals to ma, because a here is not 0, right? In this case, a is 0, so we put 0 here. So together we have T equals to mg plus ma. So that is like you have this is 29.4 from the previous case plus the 3 kilogram times 3 meter per second square, okay? That gives you 9 here, right? So 29.4 plus 9, that's like 38.4 Newton, okay? So if you got 38.4 Newton, it's correct, okay? Now third one, okay, that one is the hardest one, okay? Because we have some directions here involved. So you have one string, give a tension, another string, give a tension. And then you have a gravity going down like this, right? So this case, we have to set up our coordinate system with both x and y direction because some of the forces are not along the y direction, right? Now, this is probably the most challenging thing for you guys when you see the forces are not on the same direction. Is that right? If it's right, give me a thumb up. I mean, is this the most challenging thing? How to find the component of the force? Okay. Okay, how do we do that? Okay, again, what we're given here is these angles like 30 degree. So that means on this plane here, this is a 30 degree, okay? So, and this is a 30 degree. That means this angle here is 30 degree and this here is 30 degree, okay? So, I mean, these forces help us to, let's use one of these, okay? For example, let's consider this one, okay? So again, try to draw another picture. Draw as many pictures as you can, okay? So you have this, this is a tangent here, this is a 30 degree here, right? So you have the y component and the x component, okay? Well, based on trigonometry, tx equals to t times cosine 30, ty equals to t times sine 40, okay? Sine 30, okay? Actually, it's the same thing applies here for this tension. This is 30 degree, so this is t. Again, this is tx and this is ty, okay? So tx equal to t times cosine 30, ty equal to t times sine 30, okay? Now, you don't really need to assume that they're the same tension. I mean, I just ask it for simplicity. So maybe let's label them differently. Let's call them T1 and T2, okay? So I mean, in general, they might be different, although in this case, they turn out to be the same. So let me use this here to label them clearly, okay? So if you break them like this, okay, with these two triangles, then you can put those components back to the coordinate system. And then let me draw a little bit differently. So I have mg going down. And then you have a T1x going this way. T1y going this way. T2x, I'm sorry, this is what we call T2 here, okay, T2. And then T1x going this way and T1y going this way, okay? So I have these 5 forces or components going along each direction, okay? And then again, you apply Newton's law, okay, for the x direction, y direction. Along the x direction, you have 2 components, okay? So they must balance each other. So we have T2 cosine 30, that's the component going positive direction, minus, this let's call T2, T1, minus T1 cosine 30. That's what you have along this direction, and that equal to 0 because there's no x direction, MA equals 0, so that's 0. On the y direction, same thing. You have T1y and T2y. Okay, so it's a T1 sine 30. Yeah, shut up. Plus T2 sine 30 minus mg. So these are two components given by these 2 formulas minus mg equals 0. Okay. So these are our 2 equations from the x direction and y direction, okay? Now you see clearly that in this case, if you use the first equation here, because both angles are 30 degrees, right? So T1 actually equals to T2, okay? Because you can divide cosine 30 on these terms and then T1 equal to T2. So, and that's also, you can say it from the symmetry point of view because the angles are the same, so these 2 tangents have to be the same, but we see that they are the same indeed. Now, from the second equation, then you can solve for this, okay? So let's call them t here, okay? So in the second equation, then you have t sine theta, t sine 30 plus t sine 30, that's 2t sine 30, minus mg equals 0. So, so t equals to mg divided by 2 sine 30 degree, okay? Well, as we know, sine 30 is just 1 half. So 2 times 1 half is 1, so t equal mg. So you get basically 29.4 Newton. Okay. Now, some of you got actually pretty close. Some of you got like a 18.7. No, 19.7. I think some of you got 19.7, but that's not correct because that's I mean that's like half of it. Maybe you missed a factor 1/2 or something, so that you got that right. Well, I mean the correct answer is 29.4. Well, if I give you a different angle, it won't be exactly this. If I give you like sine 45, for example, right, then 2 times sine 45 is not going to be 1 anymore. It's going to be square root of 2, so 1.414. So you get a smaller value of t. So the angle actually determines how big the tension is. Well, I just happen to give you the angle such that the tension just equal to the mass. So what's going on here is, in the third case, you have 2 tensions, but each one of them only have 1 component used to balance the force. The horizontal component is totally useless because they balance each other. So one of them contribute 1 component, the other one contribute also a component. So I have 2 components combined, and that equal to the weight here going on opposite direction. So that happened to be the case. So you actually, I mean, that's how it works. Okay. Does that make sense to you guys? Any questions?
So
Good.
the answer to number 3 is 29.4.
Yes, that's right.
So it's
yes.
the same as 1.
Yes, as I said, it's just by accident because I give you the angle 30. If I give you a different angle, it won't be this 29.4. It'll be something else.
Oh,
okay. Please let me know if you have any questions. Okay. Again, you guys, we're done with chapter 4. You guys should be able to do your homework and everything with chapter 4. And tomorrow with the lab, we could do, when we do the lab, you guys got more opportunity to kind of do Newton's law stuff. And then we probably will do another new virtual lab because I don't know of easy way to test Newton's law just by using your meter stick or like a kitchen scale. So we probably will do it in the virtual lab again. So do you guys, how do you guys like the virtual lab from last week? Do you guys like it better or worse than the actual at home lab? Send me a message. Okay, okay. Yeah. Some of you like at home labs. Yeah, I think, yeah, unfortunately we cannot do it in our lab room, otherwise it'd be better. Or I could ask you guys to buy a bunch of devices, but that's gonna cost you more money. You know, I don't want to do that. So okay, let me try it really hard. Let me think about whether we can do it at home, but I really doubt about it because it's gonna be hard. Because to test Newton's second law, we need to measure the force, like a pulling force or something. And then we also need to measure acceleration. So both acceleration we might be able to do it with our cell phone, but it's kind of hard to measure forces unless you guys, maybe you guys can think about something as well. Let me know tomorrow. If you have a better plan, I'll follow you, or can send me email today. Figure out some way. The key here is to measure, to verify Newton's law, we need to measure force, mass, and acceleration. I think we can do the mass by using your kitchen scale. Acceleration maybe using the cell phone, but the problem is how do we measure force? You know, it not be easy to measure force at home. You know, the only force we can measure is weight, but that's too limited. You know, we cannot do better. I mean, we need to do better than that. So think about it. Let me know tomorrow, okay? I mean, certainly if you can figure out some better plans, I'll follow you guys for those, okay? Or you can send me email today, okay? Okay, I guess we finished early today. But I think that's good. You know, we finished our chapter 4, which is good. Now we're halfway of the whole semester, right? We have 8 weeks, and now we are done 4 of them. So we have another 4 to go. And we're done with our first 4 chapters. So we finished the first 4 material, first half of the material. That's good as well. And 5, 6, 7, 8, yeah. And we only done 1 test, but that's not a problem because we'll do tests more often later on as we proceed. So I think we're in a good shape, okay?